How does rock buried hundreds of meters underground end up supporting skyscrapers, bridges, and trains? The journey of iron from the mine to steel, geological exploration, giant open-pit mines, pellets feeding furnaces at over 1,500 degrees Celsius, the birth of pig iron, and its refining into steel ready to be rolled into beams and sheets. You'll see how chemistry, heat, and industrial precision transform dust into progress. Iron is not found in its pure form underground. What is extracted are minerals such as hematite and magnetite, which contain high concentrations of iron oxides. To locate these deposits, teams of geologists work with modern technologies, magnetic sensors, satellite images, and chemical soil analysis. When the existence of a profitable deposit is confirmed, mine construction begins. The most common method is the open pit mine, which consists of enormous stepped excavations. From the air, they resemble gigantic craters and in some cases measure more than 3 kilometers wide and over 600 meters deep. The environment inside the mine is a true industrial setting. Colossal excavators tear out blocks of rock, trucks the size of houses transport dozens of tons on each trip, and drills open tunnels that provide access to the deepest levels. The extracted rock is called ore and is made up of a mixture of iron, quartz, clay, and other impurities. But extracting the ore is just the beginning. It's still a long way from becoming steel. Once at the surface, the mineral must be reduced in size to separate the iron from the other materials. For this, jaw crushers are used to break the large blocks into more manageable pieces. The fragments then pass through rotating mills that further pulverize them, turning them into grains similar to coarse sand. Various concentration techniques are applied at this stage. One of these is the use of industrial magnets capable of attracting iron particles and separating them from the waste. Vibrating screens are also used to classify the fragments by size. The goal is to obtain the purest possible ore, but even then, efficiency is never complete. To produce 1 ton of usable iron, between 2 and 3 tons of raw ore can be required. This shows the magnitude of the operation. Tons and tons of rock must be moved just to obtain a fraction that will serve as raw material. The working environment at this stage is extremely harsh. Dust rises everywhere, the machines generate a deafening noise, and safety is a constant priority. Mining, despite its risks, remains one of the essential drivers of modern civilization. Crushed ore cannot be loaded directly into furnaces, as its loose form would hinder combustion and block the passage of air. To solve this problem, pellets are created, small, uniform spheres about 10 to 15 millimeters in diameter. In pelletizing plants, the ore is mixed with water, binders such as bentonite, and fluxes such as limestone. This wet mixture is introduced into rotating discs or drums, which, as they rotate, compact the material into small balls. Although they may seem simple, pellets are key to the efficient operation of the smelting process. Once formed, they pass through special furnaces where they are heated to temperatures close to 1,300 degrees Celsius. The heat gives them strength and a porous internal structure that facilitates air circulation in the furnace. After firing, the pellets are slowly cooled using forced air towers. If they cool too quickly, they could fracture, affecting the furnace's efficiency. Finally, these pellets travel by train or conveyor belt to the steel plants, where they feed the blast furnace. The blast furnace is one of the most impressive machines ever created. It is a steel tower more than 30 meters high that operates tirelessly, day and night for years. Shutting it down can cost millions of dollars, so its operation is constant and rigorously controlled. The furnace's operation combines chemistry and engineering. Iron pellets are loaded from the top, along with coke, a coal treated at high temperatures, and limestone. Preheated air at over 1,000 degrees Celsius is injected from the base. The coke burns violently, generating carbon monoxide, a gas that separates oxygen from the iron ore. This process is called reduction. The oxygen is released as a gas, leaving the metallic iron behind. As the ore descends through the tower, it changes from a solid to a glowing liquid. Pig iron, a molten iron with a high carbon content, accumulates at the bottom of the furnace. Slag forms alongside it, a viscous substance composed of impurities that will be used in the cement industry. Periodically, the liquid iron is extracted through refractory channels into large ladles that transport it to the next stage. Watching this lustrous metal emerge is like witnessing the birth of civilization in its purest form. Although pig iron is a powerful material, it is not useful in its raw form. It contains too much carbon and is brittle. To transform it into steel, it must undergo a chemical refining process in special converters. The most common is the BOF, basic oxygen furnace converter. Here, molten pig iron is poured along with recycled scrap metal, improving efficiency and reducing costs. Pure oxygen is then injected at high pressure. The oxygen reacts violently with excess carbon and other impurities such as phosphorus, sulfur or silicon, releasing them in the form of gases or slag. In a matter of minutes, the pig iron is transformed into liquid steel, which is much stronger and more versatile. Alloying elements can also be added at this stage. Chromium to increase corrosion resistance, nickel to improve hardness, or vanadium to give it elasticity. Thanks to these combinations, hundreds of different types of steel exist, each designed for a specific use. The molten steel is transported through large ladles to continuous casting machines. There, it flows into water-cooled molds, slowly solidifying into long blocks. Depending on their shape, these blocks are called blooms, thick squares, billets, thinner bars, or slabs, wide sheets. When these pieces emerge from the casting plant, they are still red hot, with temperatures approaching 1000 degrees Celsius. Taking advantage of this heat, they pass directly to the rolling mills, a succession of giant rollers that exert constant pressure. At this point, the steel is compressed, stretched and refined until it reaches the desired thickness and dimensions. Rolling can be done in two ways. Hot, when the steel is still incandescent and malleable, ideal for beams, rails and large structures, or cold, when the material has already cooled and hardened, allowing for more precise surfaces and higher quality finishes, such as those used in household appliances and automobiles. The next phase is controlled cooling, essential to ensure that the steel's mechanical properties remain stable. Depending on the final application, this cooling is carried out with pressurized water jets, forced air currents, or even oil baths. The speed at which the temperature drops is decisive. If it cools too quickly, the steel can become brittle. If it's processed too slowly, it loses its hardness. Before being considered ready, each batch of steel undergoes strict quality controls. Tensile tests are performed to verify its strength, hardness tests, visual inspections, and specialized scans capable of detecting internal defects invisible to the human eye. Only those pieces that meet the most demanding standards are packaged, labeled, and shipped to their next destination, whether it be an automotive plant, a construction company, or a shipyard. Once the steel has been shaped, rolled, cooled, and subjected to rigorous quality controls, the final stage of its journey begins: distribution to the various sectors that will transform it into works, products, and tools. This journey is not simple, as the finished steel is usually presented in blocks, coils, beams, or sheets of large and heavy material. Moving it requires precise logistics, with freight trains equipped to support tons of material, trucks with reinforced platforms that travel highways for days, and merchant ships capable of crossing oceans carrying thousands of tons in their holds. Every piece of steel, no matter how common it may seem, has a specific purpose. In construction, for example, it is transformed into beams and columns that form the skeleton of skyscrapers, colossal bridges, and sports stadiums. Structural steel allows buildings to withstand enormous loads and even natural phenomena such as earthquakes or strong winds, ensuring safety and durability. In the automotive industry, steel is transformed into car bodies, chassis, and engine components. Thanks to its balance of strength and malleability, it can absorb impacts while remaining light enough to make vehicles fuel-efficient. Millions of cars, trucks, and buses around the world depend on its unique properties. The naval and energy sectors also rely on steel as their greatest ally. The hulls of ships, submarines, and oil platforms are made with special alloys that resist saltwater corrosion for decades. Wind turbine towers, gas pipelines, and the structures of hydroelectric or nuclear plants rely on it to operate safely and continuously. In the home, although it sometimes goes unnoticed, steel is present in almost everything. In the casing of household appliances, bicycle frames, furniture, hand tools, and even the hidden structures of homes. Its versatility makes it a material that accompanies everyday life in visible and invisible ways. What makes steel truly extraordinary is its practically unlimited recyclability. A beam that supported a bridge for half a century can be melted down to become the body of a car, and that same car, years later, can be reborn as part of a wind turbine. This cycle of constant transformation ensures that steel retains its original properties, no matter how many times it is reused, making it a truly sustainable resource. Therefore, beyond its strength and adaptability, steel is irreplaceable. It accompanies humanity at every new stage, in every technological advancement, and with every global challenge. From the first blast furnaces of the Industrial Revolution to today's modern rolling mills, steel has both witnessed and played a leading role in our progress, and it will continue to be so because more than a material, it is a silent companion to human history. Steel, more than just a material, is the backbone of civilization. Without it, there would be no skyscrapers that mark the skyline of our cities, no bridges that connect entire regions, no rail and road networks that make global trade possible. Every bar, every sheet, and every beam carries with it the story of a journey that began deep within the earth, passed through fiery furnaces, and ended in the hands of architects, engineers, and builders. But what makes it truly extraordinary is not just its strength or its versatility, but its ability to be reborn again and again. A demolished structure can be melted down to become a car. A worn-out tool can be transformed into part of a wind turbine. This almost infinite cycle makes steel an eternal material, a resource that accompanies humanity in its evolution without being exhausted. From the first blast furnaces that powered the Industrial Revolution to today's ultra-modern steel plants, steel has been present at every stage of human progress. It is the bridge between nature and technology, between what we extract from the earth and what we dream of building in the future. Thus, behind every building that is erected, every ship that sails the seas, or every train that crosses continents, there is always the same protagonist: steel, a silent witness to how we transform matter into civilization.